All right, hello everyone. Welcome to another ACM seminar. Today we are very happy to have Professor Xueyu Zhu from University of Iowa. And actually he was scheduled to give a talk in the previous semester, but due to some reason, we have to have him this semester. But he recently has a very exciting work on the efficient Bayesian physics-informed neural network for inverse problem using Kalman filter inversion. So please welcome Professor Xueyu Zhu, and Xueyu, please.
Okay, thanks
Stage
for
is yours.
thanks Yunjun for the nice introduction, and I'm very happy to give a talk at a cast for my recent work. Originally scheduled to give a talk on the last semester, but due to some family reason, I have to move to this semester. Anyway, today I will give a talk on the efficient Bayesian physics-informed neural network for inverse problem. So this is joint work with my PhD student Andrew at the University of Iowa. So in the following talk, I first give the motivation of the research, and we'll talk about the setup of the problem. Then I will talk about a little bit our proposed approach, and I will show some numeric examples to demonstrate the performance of this method. Then I will draw some conclusion along this line. So the first slide, Yunjun will be kind of familiarize that because I borrow some of his slides components in these slides. So in the last few years, you probably everyone see that there are significant advances in the deep learning and artificial community. So we have seen the AlphaGo try to beat the best human Go players. And we also seen the AlphaFold, even AlphaFold 2 to predict the protein structure very efficiently. Recently, we see that the biggest thing in the March is about the ChatGPT, right? So everyone is talking about that, how powerful it is. But there's a certain amount of people will start to worry about their job security, especially in the Silicon Valley. So most people worry about that. Okay, after 5 years, then the AI might replace my jobs. So that's a big concern. Okay, even though it's technical, it's a technological advances, it also poses some of the social concern in practice. Anyway, so if you reflect what those success, most of the success story you heard that is based on the social data. The social data, you can collect a lot of those social data based on the big IT company. So they have every day they have a tons of data you can utilize that. So they tend to, it's a pretty much data-driven approach. Now, if you apply those existing deep learning algorithm to the scientific problems, so you may not enjoy the same successful experience. There are two reasons, I think. One reason is that for scientific problems, so usually we have much less high quality scientific data. You either have to take a very long time to collect data, or you have to spend a lot of time or money to collect those data. Each experiment can be expensive in time or money. Also, if the machine learning model can give you a good result, good prediction, most of the time it's a black box model. So it's you don't know why it gives you the good result. So the model is non-interpretable. So for a scientist, usually you really want to understand what is going on, what is the underlying mechanism of your problem, so that you can understand the principle behind it and apply it to the new problem in the future. So based on this concern, there's emerging communities called scientific machine learning committee or physically informed machine learning committee. They're trying to integrate prior knowledge arising from our observational, empirical, physical, or mathematical understanding of the world in order to improve the performance of the learning algorithm, particularly for the complex applications in the science engineering. So one of the representative work is so-called physical informed neural networks. So this is the citation number I recorded in half a year ago. So probably it's ready to go to about 5K. So you can see it's a very hot topic. Every day, if you go to the archive, you can see a lot of relevant paper. Either it's the improved algorithm or it's use that on practical applications. Okay, there's a lot of very strong interest into to develop this method. Okay, so the talk is along this line. So let me talk about the problem setup. We're interested in this work. So we consider the following PD model, and we have this PD differential operator. Ux is our PD solution, and lambda is the physical parameter, and we have the right-hand side function f. And we also have the boundary data. It can be included the physical parameter, and this is the boundary function we have. So the goal for this problem is that if given a limited number of measurement at a certain location and in the spatial and temporal domain, I have the measurement of the PD solution. Can we learn this physical model parameters? So that's an inverse problem setting. So for this setting, there's already a lot of traditional methods to solve the problems. However, there are some challenges of the traditional approach. Okay, so usually you need get the traditional numerical forward solver for the forward problem in somewhere, or you have developed it by yourself. Usually, if you have complicated applications or problems, those forward solver itself is quite challenging to develop. It can take several PhD to develop a very good solver. The second thing is that usually most of the inverse problem, they are using they have to use the iterative algorithm. So that means you have to run your solver multiple times. So if your solver is run one time is pretty expensive, then consider you run it multiple times, it's even expensive, right? So a more practical issue in this traditional algorithm approach is that for the real world applications, it is not uncommon. We don't know anything about the initial boundary condition, or we have partial information on the initial boundary condition. So in this case, some of the forward solver may not even able to run. So that's a big issue even in the practical setting. So that's the challenge for the traditional approach. To this end, so I'm trying to connect what happens in the deep learning community. So you can see that with the data help, you can develop a more flexible tools to help to solve this problem. So one tools we are interested in, or one popular tool to solve this setting of the problems is the PINs, physical informed neural network, especially for the inverse problem. So again, the setting for PINs for this problem is not that different. So given a limited number of measurement on U, this PD solution, we want to learn the physical parameter. That's our general goal. In this case, we also want to learn the forward surrogate of the PD solution in this case. And you can notice that we don't need the traditional numerical solver, forward solver anymore. So that's one of the difference between the setting, the traditional approach and the PIN setting. And also that would be a good, very strong advantage for PIN actually. So for PIN to solve this problem, usually PIN will approximate the PD solution by a neural network U tilde parameterized by theta. Okay, besides this approximation and the data we have, we also have some free information we call the virtual measurement. Because we have the PD setting, so in this case, if I plug in if I have the real solution, if I plug into the differential operator, actually equal to my right-hand side f. So that's f is usually given by the problem. So that's a free data we can use. We call that the residual data. And we also have some boundary condition function. So we call that boundary data. Okay, so these are the two pieces of information we can utilize that. Now you notice that we have the original physical parameter we need to learn. We also have the parameter for the neural network, or the weights of the neural network need to be learned. So to learn those parameters, we call that this concatenated vector to be the vector concatenate both physical parameters and neural network weights. And to learn this parameter, we usually need to train the following laws to estimate that or infer that. So usually have three components. The first one is the real data measurement, the data misfit. And the second component is about the PD residual. So if you plug your residual, the PD solution, approximate PD solution here, we hope that the difference between this operator and right-hand side is not very large. right? Not very. So hopefully it will be to very small after training. And the last component is the boundary data loss. So you can see the last two term is relevant to the underlying TDE structure. So this is the equation and this is the boundary data, right? Okay. Now, what advantage we can or benefits we can gain from using PIN to solve the inverse problem? The first thing I already mentioned that we don't need the forward solver, develop a forward solver anymore. It takes a long time. Oh, it's very expensive to run those forward solver. And also for PIN, it's relatively easy to implement and adapt to a new problem, a new setting is also relatively easy. For forward problem, you can take an undergraduate from 1 day to one week to make it work. Okay. The second thing is that the PIN here, you can see I didn't use any mesh-based method compared to traditional approach. So usually you have to get a mesh and do the numerical discretization for your forward problem. So if you have a high dimensional problem, 3D problem, even in the kinetic equation, you may have 60 problems. So that can take a lot of memory or mesh point to get a reasonably good result. So in this case, since it's a mesh-free method, that's a potential, you can get a potential saving for the high dimensional forward problems if you have in the inverse problem setting. And last point is that most of the PIN library is building upon the TensorFlow, PyTorch or JAX, those high performance deep learning library. If there's a major updates or advances in those library, you can easily take advantage of that. So those are the main advantage we can see for PINs. Okay. However, the standard PIN I talked about just now is deterministic version of PIN. So they only provide the point estimates without any uncertainty estimation. So also, if you have noisy data, you have a data poor case, you have much less data or sparse data. So the result, the estimation is not very robust. So in the cases, if you have a high stake application, for example, auto driving task, so the uncertainty, reliable uncertainty, and the robust estimation will be very useful for the downstream decision making, right? For example, when you're driving, so there are some object, how much percentage it can be. I can give a prediction that's a human or that's a dog, but I also want to give a standard deviation, say how much, or I'm not sure about this my prediction, right? If I'm quite not sure about the prediction, I should ring the alarm to the driver to let them to check that, right? So there's a practical needs for developing the reliable uncertainty quantification for those neural networks, especially for PINs. Okay, so based on this motivation, so people in the PIN community, they are developing the Bayesian version of physical informed neural networks. So the idea is pretty straightforward. Okay, instead of treating in the previous version, we're treating the neural network parameters and the physical parameter as the deterministic variable. So we use the standard optimization algorithm, SGD or DAM, to optimize that to get a parameter value. But in this case, in order to account for the uncertainty, we will treat those parameters as a random variable. Okay. Now, if I assume that we have the prior information of those parameters, and if we provide the constructed likelihood function, we can get a posterior. So the likelihood function actually here contain all of the information similar to we discussed in the deterministic version. So you can see the first likelihood is the data likelihood. So we have the difference between the data and our prediction is follow the Gaussian likelihood. And the next component will be, next term will be relevant to the residual, PD residual term. We also assume it's Gaussian. And the last one is the boundary data loss likelihood function. Then we combine them together, that's our likelihood function, okay? So now, based on the prior and the likelihood, where we construct the prior. So the question is that, based on this prior, how can we estimate the parameters, or how can we infer the parameters? So the inference problem, this is an inference problem. Actually, it's pretty hard inference problem. It's a high dimension problem. You can think about that. So besides the physical parameters, we also have many neural net weights need to estimate. So let's say if I use around 2 layers, 50 hidden units, easily the parameters we need to estimate is about 5,000, right? That's quite a, well, in terms of neural network size, it's not very large if you look at the gradient-based method. But in terms of the high dimensional posterior space, parameter space, that's quite high, right? Okay, so actually this is a pretty challenging game to play in the literature. So if you look at the literature to check the existing approach, there are several major ones. The first one is HMC, the Hamiltonian Monte Carlo method. So this approach is the golden standard method for inference problem in Bayesian neural network itself, not just the BPIN, okay, in the Bayesian neural networks. So in terms of the inference quality or inference accuracy, that's the best theoretically. However, it's very expensive for high dimension problem. So even though I mentioned that I only have a 2-layer, 50 hidden units for each layer, so this problem is very high dimensional inference problem. It's pretty difficult in terms of cost. Now, you can also, people also consider MSMC, but MSMC it's an independent dimension, but the convergence is very slow, okay? And those two are the major tools using in the traditional Bayesian universe context. They belongs to the one category, so-called particle method. So they have to generate a lot of ensemble members to approximate the posterior. But there's another type of approach, it's called a variation approach. So it basically choose the class of a family class of the distribution to approximate the underlying target prime. So the good thing about this variational inference approach is it's computational efficient or preferable in the high dimension problem. But the disadvantage is less you get a less satisfactory inference result. The inference quality is a little bit worse. Then people will think about that, okay, variational approach is fast. Particle-based methods are accurate. Can we combine them together? So that's one of the combination is the called SVGD. So again, a computational is favorable for the high dimension problem, but it tends to estimate the uncertainties of your target of interest due to the collapse of the ensamples. Also, there's one general observation we can make is that most of the existing popular inference approach, they are gradient-based method. That means that you have to compute the Babel propagation and you have to update your the parameters. The gradient-based method itself is pretty expensive for the high scale, for the large scale networks. So you can see that in the GPT, they have trained a super large model. They have to use the very good hardware, the latest hardware, let's say the 800 NVIDIA graphic card in order to do the efficient training. But that's only from the hardware perspective. It's still very expensive to train the large scale network. So the question is it possible to develop the efficient inference algorithm based on for this Bayesian physically informed neural networks, while providing some of useful uncertainty quantification for the underlying output of interest? Okay, so based on this motivation, I want to talk about our proposed approach. So before I talk about this approach, I want to talk about one setting. This is an old setting in the literature. It's called the this is called the Bayesian inverse problem. So for Bayesian inverse problem, the setting is pretty simple. I'm given a limited number of measurements, we call it Y, and we want to infer some of the physical parameter for some physical model. So this parameter will be this C. And G is in the literature, we call the observation operator or parameter to observation map. So this G operator usually is corresponding to the traditional forward solver you have to solve. It can be very expensive, right? Very expensive. And there's another component that I assume that between my model, the observation model, and the real measurement, I have some error. We'll try to take account of that and represented by eta. And this eta, in this case, we assume that it's follow the Gaussian distribution and with the observation error occurrence matrices. And if I assume that we have this prior information of the parameter we want to estimate, then we can construct a prior the posterior based on this likelihood to construct prior. Okay. So with this setup, there's a lot of method to solve this setup. Recently there's one popular method so-called Ensemble Kalman Inversion method to solve this problem. The EKI method, so-called EKI is particularly efficient for the high-dimensional problems. Okay, so that's again, this is our setting. In the EKI setting, instead of solving this problem directly, they slightly change the setting. They convert this observation, instead of just looking at the observation model, what they did, they introduced artificial dynamics for this observation. So we have the original observation model, okay? And so he add a artificial evolution model, a dynamics model for the parameter itself. Let's say at S-1 iteration, I add some noise to the data, perturb a little bit that, and I get a new value of this parameter at S iteration, and plug in back to the observation operator, and I get a predict observation, and this one will corresponding to the data, with the real measurement we have. Okay, in order to match to the original setting of the Bayesian inverse problem, so we especially assume that each iteration will have the same data here. Okay, so in order to match this original setting, so once you have this setting, we reach to a new model, not a new model, it's an old setup, it's called a state space model. So for this space model, there's all of the data assimilation tools. They're trying to solve this kind of problem. Particularly EKI is pretty robust to solve this kind of problem. So EKI will place a Gaussian assumption on this prior by approximating it by J particles. This J particles usually is much smaller than the number of parameters you want to estimate. Okay, we want to approximate this prior iteratively. Every time I will update using the Kalman update. This is a famous update in the DA community to get the next step in sample to approximate this prior. Okay, let me make it more concretely. So at I-1 iteration, and for J's particles, I will perturb a little bit that with the noise, and we'll get a new value for this J's particles, and we'll plug them in that the observation operator, and we'll get a new predict observation, and then I can compute the sample mean for the parameters. I can also compute the sample mean of the predict observation. I can also compute the covariance matrix for the predict mean. I can also compute the covariance between the parameters I estimate and the predict mean. So based on those information, I can use the Kalman update to update the parameter to the next iteration. Okay, now you can go through this iteration round and round. Hopefully, after enough number of iteration, we will get a reasonable estimate to the posterior. Okay, that's the major idea here. Okay, now you may wonder, okay, why we should care about the EKI? I didn't see any connection or advantage to using that for our BPM problem, right? So let me introduce some of the properties. Can I ask a quick
question?
Sure.
Here, I'm wondering, the choice of J seems to be quite crucial for many desirable property, for example, convergence rate or how many iteration to be used until you get a converged result. Then in this context, I'm wondering if J also can be subjective to some uncertainty so that we can quantify it along the way so that every iteration that somehow covariance also being computed in the Kalman update way so that we can estimate J for the next iteration. Have you ever thought about or aware of this kind of approach?
So far, I haven't seen anyone did that, because every time you did that, you have to resample. Let's say if you increase the J after another next iteration, increase the J number, you have to reinitialize or resample another ensemble member.
Right.
Right. So increase that there might be some way, but traditionally I didn't see too much work on that. Maybe that's a good idea, I would say.
And another one more thing here. So assuming G is linear, I can see that why this kind of
G is an observation operator, you mean?
Yes, G
Okay,
observation operator. Assuming G is linear, I can see that why this step makes sense, because basically covariance wants to measure the linear relation between two quantities. So in that sense, if G is nonlinear, do you think it make sense to think about somehow introducing nonlinear operator to get some covariance operator? For example, like instead of like identity, so here, let me a little bit annotate. So instead of here, this is just a linear relation, but we can do some Connell trait. That being said, we are applying some nonlinear operator on the top of it so that we can make a nonlinear relation in a certain way. So
yeah, you have a kernel version of that. Actually, SVGD quite similar to that. Yeah. There's another method that is also used the kernel idea.
Oh, okay.
Yeah.
Thank you.
We can discuss about that. There are versions of that. However, in that case, the cost actually is not small. I will point out that.
Oh, I see.
SVGD, usually you rarely see that run above 100 particles because it's very, very expensive.
I see.
I see a lot of applications using 10 particles. But using 10 particles, you probably cannot, to predict the mean, probably it's okay. Standard deviation, maybe, but for predict distribution will be far from enough, 10 particles.
I see.
Yeah. Okay, I think that's a good question. They do have a consideration that, but not in the traditional DA community, but in the other community, they're consider that. Yeah. Okay, so then question is that why we care about the EKI? Can they solve they have some properties relevant to our problem. So let's say the first thing you will notice that if you go to the main EKI algorithm, you can see we didn't compute any gradient information explicitly to update our formula. That's a big advantage. That means that we don't have to go through the backpropagation in the neural network. Okay, that's the major cost even in the neural network. Second thing is very easy to implement. The core part may be less than 10 lines of the algorithm, and it's for most of the part of the algorithm is inversion parallel. So if you can take advantage for the architecture, so you can do that pretty efficiently. Two major bullet points for EKI is that its complexity is linear with respect to the number of parameters you want to estimate. So that's very good news if you have a high dimensional inference problem. So for example, in the neural network setting, usually we will have the overparameterized the setting. Even though in the, let's say, in the two layers and 50 hidden units, we have 5,000 parameters need to estimate, right? So in this case, so the complexity is pretty good, have pretty good scaling with the dimension of the problems. This, we are essentially mitigate the issue of HMC, okay? And for another issue is that since we add, in this step, we add the random work here or perturbation here, so it's tend to avoid the ensemble collapse happens in the practical setting, which is one of the major issue for the SVGD, right? So this is a two major issue on the existing method, sort of can bypass this issue. Also in the practical problems, we do observe that the EKI has a very fast convergence, usually around 100 iterations, and then we can see the convergence. And in the literature, the EKI usually is also very robust to noise and can provide a meaningful answering quantification. Okay, that's the motivation why we want to use an EKI. Now the question is that, okay, you talk about the BPIN setup, you talk about the EKI setup. How do we apply EKI to the BPINs, right? Seems that there's no connection between each other. So let me recall that. So this Cauchy operator, so it is a concatenated vector containing the physical parameter you want to estimate and neural net weights you want to estimate. Okay, and in the pin notion, so we denote this forward surrogate to be the U tilde parameterized by theta, and we have the three data set. One is the real measurement. The other one, we have two virtual measurement. One is the residual data, the other one is boundary data. And in order to match the EKI setting, if you look at the EKI setting, So basically, if you have this, you can identify what is your the observation model you're done, right? So identify what is your real measurement, and identify what is your observation operator. So let's try to map that to the the pin setting. So in this case, assume that our the measurement our measurement vector has a 3 components. The first one is the real data set, real measurement. Then the corresponding observation will corresponding to the neural net forward surrogate, which is U tilde. Okay, that's called a GU. You can say GU is defined as the neural net evaluation at different the collocation point corresponding to the real measurement. And the second component for the measurement is the right-hand side F. So the corresponding observation operator will corresponding to the left-hand side of the equation, which is the neural net. That's the differential operator of the neural network. Evaluate at all of the residual point we want to evaluate. Right. This data is actually virtual. And the last piece of the component in the measurement is the boundary data. Right. The corresponding observation operator will be the neural net first forward surrogate evaluate at those boundary point, and you can get a prediction of those data. That's prediction, the predicted observation. Okay. Now with this identification of those notion for both pin and EKI, now we are theoretically we can apply we're ready to apply the EKI for this problem. Okay. Now I want to emphasize that in this case, since we are using EKI to approximate to the inference task for pin. And for pin, we don't need any forward solver. So compared to the traditional EKI setting, we don't need any traditional forward numerical solver anymore. Right? In the traditional EKI setting, they do require the very sophisticated the PDE solver to solve that problem, right? In order to do the inverse problem. In this case, since we're using pin framework, we're essentially trying to learn the forward surrogate and the physical parameters with the soft physics constraint here, especially through this the residual observation operator. The second thing we want to mention that since the forward surrogate is very cheap to evaluate, actually we can run a lot of ensemble. We can draw a lot of samples. This will help to significantly reduce the sampling error. So usually if you see the EKS literature, so they usually run hundreds of samples because the underlying assumption is the underlying classical solver is very expensive. So we can't run too much of the samples, right? But in this case, we can easily go to thousands of samples, thousands in sample members. Okay, so the sampling error will be dramatically reduced in this case. Okay, so there's another practical issue for this EKI in order to make it work more efficiently. So it's the stopping criterion. So it's an iterative algorithm. We talk about EKI take a number of steps to approximate the posterior by the particles or ensemble members. However, there's some trade-off in this step decision where to stop. So if we have more steps, so it means that we are exploring the high dimensional posterior space, parameter space. However, if you do more iterations, then you will pay more computational cost or price in order to do this exploration. So when to stop, that's a trade-off. Okay, that's a trade-off question. So you have to make your decision. And in the traditional EKI literature, so one of the standard stopping criterion is based on the discrepancy principle. This is the following principle. So basically what they do is that they compute the difference between the measurement, real measurement, and the in-sample mean of predicted and measurement multiplied by the observation error covariance. And if this value, the norm of this value is smaller than a certain threshold, and we will call that, okay, we can stop here. Okay, that's one of the standard approach in the EKI literature. However, in this setting, different from the EKI setting, original EKI setting, usually they only have the data in this the real measurement and the real measurement data. But in our case, we also have a virtual measurement data. Then the virtual measurement data also contain the PD residual. Then in general, since we are learning the neural net parameter jointly with the physical parameter. So that residual is evolving. We don't know it's not very clear to say what is this value, the eta value, especially related with the residual. So if you use that to as a stopping criterion, in practice we observe it's not very effective. It may not stop at the red places. Okay, so we propose a heuristic approach based on this discrepancy principle. So at the S iteration, I will compute this discrepancy indicator, the value, and then I will at S iteration I will count all of those discrepancy indicator value at the previous W iteration. Among all of those, I will compute the difference between the previous iteration discrepancy value with my current iteration. I compute this relatively difference here, and I will find the largest the relative change. If it's smaller than tau, let's say 5%, I will call it stop. So in practice, we observe that this one is more will be more effective than the standard stopping criterion. Will make it work. Okay, we'll stop at reasonable places. Okay. Okay, let's put everything together. That's the pseudo algorithm for the whole algorithm. So initially, you will have to assume that we have a prior. We can initialize that all the parameters for different particles. And at S iteration, I will perturb the J's particles with some noise and update that. And then evaluate this value for its corresponding the observation operator, get a predicted mean, and I can compute it I do this for every particle, J particles, and then compute the sample mean of the parameters of the ensemble. I can also compute the sample mean of the predicted mean of the ensamples, or predict the observation of the ensamples. And then also I can compute the corresponding covariance matrices for the predict observation and the covariance matrix between the parameters and the predict mean. Okay, with those information, we can apply the famous Kalman update formula to get these parameters, right? To update the parameters. Now we also need to check the stopping criterion at each iteration. Once they reach the criterion, where we can terminate the algorithm and call that's the estimation we want. Okay. Hopefully it's a desired approximation. Okay, with this, I introduced the major component of the algorithm. There are other details I didn't mention, but I want to show you the performance of this method. The first example is a 1D linear Poisson equation. And in this case, I have this K parameter I want to estimate. I also have the boundary data. It also shows up in the boundary data. One of the boundary, red boundary. So in this case, since this one is a linear equation, we have the exact solution for this problem. Okay, and in this case, I will get 8 real measurement for the solution, 2 boundary condition data, and 100 residual point in this case. And to approximate the PD solution, I will use 2 hidden layers with 50 hidden units. This is corresponding to around 5,000 parameter I need to estimate plus the physical parameter. Okay, it's a very high dimensional problem. So in the EKI setting, I will use 100 particles or ensemble members to in the EKI setting in the algorithm, and I also will compare with the HMC based BPIN, which is the state of art method in this field. And in this case, I mentioned that since this is a linear problem, so we can construct a reference posterior distribution of this the estimated parameters based on those given data, because it's a linearity due to the linearity of the problems. So here, I will pollute this data with some noise. In this case, the noise level is about 0.01 with Gaussian noise. And the blue line is our reference reference posterior distribution based on the data we have. And you can see the green line is the HMC based BPIN method. And EKI will be the green-orange line. So you can see roughly the performance roughly the same, okay? And oh, I want to mention that, so in this case, to get those distribution, we use both 100 in sample for EKI and HMC, right? I want to draw in the samples for EKI and HMC. And here I show you the confidence interval we estimate for the parameter we want to estimate for the K value. So the ground truth is 1. So you can see with this one, with this noise level, so we can capture this ground truth with 1 standard deviation for both methods, for EKI and HMC. Meanwhile, here I also show you that the corresponding posterior mean error for the forward problem, and you can see that this one is less than 2% of the error. And also I show you the posterior mean error for the parameter estimation. Here you can see that that's even better. In this case, it's less than 0.2% of the error, right? So both methods are, I would say, roughly same performance. But the work time, if you compare the work time, EKI takes around 5.8 seconds, but HMC takes about 46 seconds, right? So in this case, I would say roughly 9 to 10 times speed up for this problem. You can see that this iteration roughly 100, order 100 of iterations, right, for EKI. And I present this problem because in this case, this is an easy problem. It's easy problem. We can construct the reference posterior distribution, so we can directly to compare to access the inference quantity or accuracy for both EKI and the HMC method. So far, we can see that for this simple problem, they have a similar inference performance, but EKI is roughly 9 to 10 times speed up faster than the HMC-based method.
Can I ask a quick question here?
Sure.
So, okay, seems a little bit counterintuitive to me, given that, so it seems like to me that in this particular problem, with respect to K, the G operator is linear when it comes to with respect to K. Is that correct? And if that is the case, then I sort of like believe that the estimation error for K should be better than estimation error for the nonlinear term. But when it is compared with the HMC, it seems quite surprised to me that the error on K is a little bit worse than HMC. Can you a little bit comment on that? Why this might be the case, given that Kalman feature inversion? Yeah,
there's also for this one, there are also hyperparameters we haven't seen. So in the EKI, so you also have those I would say the observational error covariance matrices. You have to define rightly. That's the hyperparameter you have to tune. Right. In general, we don't know in the original EKI setting. So at least for the R part, the residual, we're not satisfied exactly. Right. So in the traditional EKI setting, so they are using the traditional solver, they satisfy that exactly. Right? So at least up to numerical accuracy. So in that case, they have a very strong constraint there. So that will cause, I think that's one of the difference in these cases. Right? Okay, that's just my guess. Maybe there's other reason. So there's still need, I would say this is roughly similar performance. But you can see that in the forward solution, well, the EKI also doing better job. So I would say this is roughly the same scale. If it is less than 1%, probably for inverse problem, nobody care about that. Yeah. Usually,
is this all time? Is it all? Yeah, go ahead.
Yeah, go ahead. So what time is what?
So wall time is measured with the when you run it on GPU or CPU?
On GPU.
Okay.
Yeah.
Thank you.
Okay, the second example, we slightly change the setting. So we want to consider this nonlinear problem, the 1D Burgers equation, and we want to estimate this mu, the viscosity, and this is our initial condition, this is boundary condition. And in this case, you can see that we have used 100 the measurement on U. That's this black dot corresponding where I sample data for space and temporal domain. This is the corresponding forward solution. And B is the corresponding the boundary data we use around 75. And the residual data we use around 100 data. We will use the same architecture, same number of ensemble member from the previous examples. And here, again, I will first show you that, okay, I also will pollute the corrupted data with the different Gaussian noise level. This is the 0.1 and the 0.01 and 0.1. And we compare the posterior mean error for both forward solution. You can see roughly less than 5% of the error for both noise level. And here is the posterior mean error for both the parameter estimation error. So you can see that in this case, now you can see that it indeed is roughly the same level. Okay, the accuracy level. So roughly is the total consider the smaller error noise level, it's roughly 3% of the error, and for larger noise, roughly 8% of error. That's in general, that's a pretty good result for the inverse problem. And if we compare the work time, so that's more interesting to say, right? So here we roughly for EKI we use 6 seconds, and for HMC we use 60 seconds, roughly 10 times speed up, right? For roughly the same number of inference quantity. And again, if we pay attention to the iteration, roughly 100 iteration or 100 iterations. And here again, I show you the one standard deviation, the confidence interval corresponding to one standard deviation. You can see in this case, I would say roughly they have the similar mean, but HMC tend to give a little bit more conservative estimation on the spread, right? So you can see EKIs tend to be a little bit narrow in the standard deviation here, but roughly you can see that it's close to the posterior mean. Okay, then to further show the uncertainty quantification estimation, so I compare the posterior mean for the forward problem for EKI and HMC based method, and for different noise levels. So you can see that for posterior mean for EKI and HMC at different noise level, the posterior mean agree well with each other for both of method. And similar thing, we can see that in the standard deviation over the spatial temporal domain, I can see that roughly at different noise levels, you can see the distribution for both problem, but both approach at different noise level, they are look similar to each other. We also draw, plot the absolute error between the posterior mean and ground truth. Now you can see for this one, you can see this error at different noise level tend to correlate well with the standard deviation. For example, where you have a larger uncertainty standard deviation here, you tend to have larger error around this region. It's not a one-to-one correspondence, but the bucket behavior will be pretty similar to each other, right? So this indicates that for this example, at least, is the uncertainty we provide by both approach can be served informative error indicator for the underlying estimation. Okay, but remember, EKI for this problem is 10 times faster than the HMC based method. Okay. The last example I want to show you here is a 2D diffusion reaction equation with a source location problem. So in this problem, I know lambda, I know f1 function. This is existing. This is a known function, known parameters. But for the f2 function, which is the source function here, I know the structure of this function, but I don't know the corresponding location of the problem. Okay. So this is I have three terms in this F2 function, and also this is a 2D problem, so I have a 6 physical parameter to estimate. Plus, I have the same, I use the same number of same neural network architecture to approximate the forward problem. So I will use around 5,000 parameters I need to estimate here. Okay, and in this case, I use 100 data for the U, 100 data on the boundary, and 100 data on the residual. Okay, you can see where I sample those data points. in the 2D spatial domain here. And here you can see here, I first show you the posterior mean error for different noise level. Now, for the forward solution, you can see for both cases, for both noise level, both methods can reach to the error roughly under 2% of the error for forward solution. And for the parameter estimation, we have 6 parameters we need to estimate. Now you can see for smaller noise level, basically you can reach the error smaller than 3% of error for the parameter estimation. For larger noise, EKI doing a reasonably good job. So most of them are less than 3% of error. I would say HMC-based methods roughly have the similar performance, except that at X3 coordinates, slightly worse than the EKI, but it's still roughly the same performance. Well, more interesting if we compare the wall time. So this one around used 2.5 seconds for EKI, and for HMC roughly 70 seconds. So roughly 30 times speed up, right? And in this case, you can see how much iteration we used using the corresponding stopping criterion. So roughly 60 iteration. This is roughly 70 iterations. So if you stop earlier, that means you can save more computational time, even, right? Okay. Now, if we compare, if I show you the posterior mean distribution, posterior mean for the forward solution, you can see for both noise level, for EKI and HMC, their posterior mean agree well with each other, similar to the previous example. For the standard deviation over the 2D domain, so I would say they don't not as good as the previous example, but particularly for the smaller noise. But for larger noise, you can see that their bark behavior will be roughly the same. Not, of course, not the details level. Okay, but if we compare to the posterior mean, the error between posterior mean and the ground truth of the forward solution, then you can see that both standard deviation or uncertainty not that well correlated compared with the previous example. However, now if you look at a larger noise error, so you can see that so they still capture some of the bug behavior. For example, we know that in this region, my uncertainty is large, but you also notice that in this case, my error is relatively also large in this region. For example, in this place is a very high uncertainty, and also you can see that in this case, it will have very high error here. So in general, for this example, the UQ, the uncertainty estimation is not perfect. Actually, it's for both methods, EKI and HMC based, but both methods actually can capture some of the feature of the underlying problem. For example, if you have in the region you have larger uncertainty, you tend to have larger errors. Okay. Okay. Of course, not very detailed the uncertainty estimation as the previous example. Okay. With that, let me conclude what I discussed today. I introduced the efficient inference algorithm for Bayesian physically informed neural networks. This is the first work to imply EKI for the inference tasks in BPIN's framework. And our approach through the example, I show you that in those examples, our proposed approach delivered the comparable inference results for the physical parameter estimation and learning the forward surrogate compared to the HMC-based Bayesian physical informed neural networks, but with around 10 to 30 times speed up for getting the same level of method, same quantity of method. And also we can see that usually the EKI approach can converge roughly around other 100 iterations. That's pretty fast. Also, you notice that we do see that in some of the examples, the EKI approach didn't provide a very detailed UQ. But if you want to, if you have the better UQ estimation, the EKI approach can still provide a very potentially good initialization for other inference algorithms. For example, the HMC, usually you have to do very long time for the burning time. So you can save that time for using the EKI as an initialization. Okay. So currently we are trying to investigate more the approach from theoretical perspective, what is the good way to get best performance or relatively optimum performance. Also, we're testing the algorithm in the situation is when we have a much larger data set and much large network. In this setting, we tend to test the cases. We have noisy data, we have a data poor scenario. The network is moderate size, but not very large. Okay, we want to test the performance, see when the method will break. Also, we are trying to say that, okay, as Xueyu mentioned, this is a linear problem. That's not very challenging. So we are trying to test that on some theoretically challenging inverse problem in the different application. For example, in the geophysics, based on preliminary result, we are still seeing the promising result. But we hope that we can report this the more interesting examples, more challenging examples in the near future. Yeah, thank you. And if you are interested in the detail of this method, I uploaded this. We already uploaded the preprint in the archive, so you're welcome to read that. And if you have questions, I'm very happy to answer that. Thank you.
All right, thank you very much for a very interesting talk. Are there any questions from the audience to the speaker?
Can I ask a question?
Sure.
Oh, so thank you for the interesting talk. I also work with Bayesian neural network.
Oh,
so
okay.
it is really interesting. Oh.
Uh-huh.
So I have one quick question. As
Sure.
Professor Shin mentioned, the inference is exact only when the observation operator G is linear. But in the case of Burgers equation, it provides a good result, although it is non-linear. Is that right?
Yes, theoretically, that's the truth. Actually, so there are literature talk about this setting. So even though EKI should work perfectly, I would say, in the linear setting, but the non-linear setting, they are asymptotically biased. But in general, practical problem, if you look at the literature, people still apply that into the non-linear setting. Usually, they get the reasonable good result. Most of the, I would say, the estimation or the theoretical analysis, they start with nonlinear setting. Okay, they said that, okay, if this step is, if you have the nonlinear operator, and then this step it's not very accurate, right? But they don't quantify how much it is not accurate. Also, compared to the noise level you have, or the noise level you have, or the ill-posedness of the problem. So I think that's the major issue even in the original problem setup. That might cause more problem. I don't have a definite answer. That's my understanding of the problem. It can be further improved. I think this is a more interesting question because in the traditional EKI setting, they're usually only working with the traditional numerical forward solver. That's like, for example, finite difference solver, finite one element solver. So their solver is pretty good. They are good in terms of the accurate assertion to you can see the convergence. You can show the formal proof of the accuracy for the forward problem. However, if you have complicated problems, you have to develop that solver first, right? That takes a quite long time. Also, if you have some of them, the solver is so good. So if you have, for example, if you estimate a parameter, which is let's say it should be non-negative, and you predict when you answer your algorithm, you get a negative value, and you put it into the original numerical solver, and then it will blow up. Maybe most of the time will blow up. But in the pin setting, I'm doing the fitting. I'm not doing the formal solving. So you tend to have less step problem. So in terms of that thing, I would say in pin setting is much robust, I would say. Right. So there's a lot of setting difference compared to the original one, the EKI setting or the operator setting, right? And also the operator you mentioned that is for the approximation of the original PD set, the setting, right? For this one, I think the more nonlinearity actually is in the neural net approximation. The neural net approximation it's a composition function, and you compose in the middle. You also have the nonlinear activation function. That's much more nonlinear, right? If you think it that way, right? But it seems that based on our current experience, it seems to give a reasonable good performance. So this is also intriguing for myself, right? So there's a lot of interesting theoretical questions to be asked. So this first work is essentially showing that it's the feasibility of this idea. Of course, there's a much more deeper question can be asked, which also we are interesting to explore. Maybe we can talk about little bit later on to discuss within along this direction more deeply.
Okay, thank you for your kind answer.
Okay, thank you.
Yeah, that's very interesting question. Are there any other questions from the audience? Have you met Professor Chang-Ok Lee before?
Maybe not.
I think that Professor Chang-Ok Lee is joining us today. Maybe let me introduce him to you. 이청 교수님 안녕하세요.
Yeah, I'm here.
Hello.
Yeah. Hello. Yeah.
So he has been at KAIST for many years, and he is the master advisor of Herring Cho, and he served as the ACM president. His term just ended as of the last year, but yeah.
Nice to see you.
I just wanted to introduce you to the Professor Lee.
Yeah.
He's also working on the inverse problem, image processing, and etc. So
I don't know, because I feel that the real advantage for PIN, at least in my side, is on the inverse problem. So maybe that's a good revenue for the inverse problem even. Yeah.
Okay, so if there are no more questions from the audience, let's thank to the speaker again for the great talk.
Okay, thank you. Thank you for the invitation.
Okay, that's it for this week's ACM seminar. And next week, we're going to have in-person talk from the Professor Oh from Chungnam University, so that we'll see you in person next week. Thank you for joining us today.